Welcome to Anton Teaches Packy AI, week number 2. I learned a ton last week. I think we got a bunch of feedback that this is something that people were interested in. I think I'm not the only person out there right now who's seeing everything that's happening and wondering exactly what's going on at a level deeper than like, whoa, this is really cool. So I'm glad that we're back for number 2. We teased the paper last time. We're doing DeepMind's training compute optimal large language models. Anton, what's this paper about?
Yeah, so last time we covered transformers, which are the basis of the large language models under discussion in this paper. And when those models came out, there was this big question, I have so many GPUs, I have so much time or energy or whatever I want to dedicate to training these models. How do I optimally allocate that? Like, how do I figure out how long I should be training for? How do I figure out how much data I need in order to increase performance to the point that I'd like? Or how do I best utilize the compute that I have available is the real question that people were asking. This is actually not the first paper to tackle that question for large language models. There's another paper back in 2020, and I have it here somewhere. It is, and I'll give you a
Kaplan
link.
et al. That I've seen throughout the paper.
That's right. Referring to Kaplan, the 2020 paper that was out of OpenAI, if I don't have my wires crossed. It was called Scaling Laws for Neural Language Models, right? And this was the first paper. The Kaplan's paper was sort of one of the first papers that was really investigating how do these things actually scale? Like, if we add more parameters, does it get better? If so, how much better does it get? How does that scale with how much compute we run it for? And so they came to a few conclusions. And what they kicked off was basically a race for the largest language model. So a large here means like how many parameters does the model have? Right? There's a few things called out here in this paper, the training compute optimal language models paper, that like point to like these models of ever increasing parameter count. What's interesting about it is like, okay, well, everyone was focused on the parameter count. Not many people were focused on the like the compute cost or the data. And you start running into these questions where you start wondering like, well, actually, like there's a finite number of GPUs in the world, and there's a finite number of them that I possess. And besides that, like these things are very energy intensive to train. GPUs are not cheap to run in terms of power. And so, people wanted to revisit this question. And the importance of this paper is basically says, okay, actually, you know what? All these models with these huge number of parameters, they're undertrained, because we've discovered that what actually matters is if you're going to increase the number of parameters of your model, you're also needing to increase the amount of data that you're feeding it for the same amount of compute in order to like actually increase performance. So that's kind of the importance of this paper. It introduced what are accepted to be today the scaling laws for transformer-based large language models.
You anticipated the kind of next question that I was going to ask, which is it talks about the trade-off between making models bigger and training them more. And so just to set the kind of vocabulary, bigger means more parameters. Yes. Training them more means throwing more data into them. Do I have that right?
Yes. Yes. So basically what you do is you say, okay, we're going to hold the amount of compute that we have fixed, right? And here the value for the compute, the way that they measure what compute is flops, it's floating point operations, right? So we're going to do this many floating point operations and train the model for that many floating point operations. And so how much data versus how many parameters, given that we have this many floating point operations to perform, should we use?
And floating point operations, I think we touched on last time, but that then translates into cost and energy. Like, it's one of the questions that I had when I was reading this is like, why does it matter, right? Like, if you're OpenAI, you kind of have the ability. I mean, like, I've seen them lead a couple of fairly big funding rounds. So it's not like money's an issue at OpenAI. They have the partnership with Microsoft. Like, why does it matter and I guess DeepMind has even deeper pockets with Alphabet. Like, for these guys, why does it matter to have the optimal setting versus just throwing more parameters at it?
Well, at this kind of scale, even if you have extremely deep pockets, there's a finite amount of compute you actually have access to. And also you are thinking about like, how much energy am I actually using to like train this? Is it worth it? Like, you do have to ship a model at some point. You can't leave the GPUs running forever, like trying to make it better, because if you do that, by the way, other people will come up with new architectures and you will want to stop. If you spend too much time on one thing, something else is going to catch up to you and just outpace you. Even if you hypothetically have access to as many GPUs for as long as you want, you probably still don't want to train forever.
It reminds me of the like classic disruption theory graph, where if you spend like too much time up market focusing on like the fanciest customers with the most needs, somebody's going to do something really, really well for the low end and then catch you just with a steeper trajectory.
Just as an example, right? And so you really want to know what optimal is. You want to make sure that you're at least in the ballpark of what you should be doing given the resources that you have. And that's the way that Chinchilla frames things. It says, given the budget that you set, so you can set the budget, how much data and how much compute should you use to have in some sense, optimally trained model?
You mentioned Chinchilla there for the first time.
Yes.
What is Chinchilla and why is it so much better than Gopher?
Right. Yeah. So Chinchilla, Gopher, we're going to have to give a lot of context here, I think, so people don't get confused. So a lot of people call this the Chinchilla paper for short, because training compute optimal large language models is a mouthful and Chinchilla is pretty short. Chinchilla is the model that DeepMind trained based on the results that they got out of finding these empirical laws about scaling. And the reason that they relate Chinchilla to Gopher, because Gopher was trained for the same amount of time and has more parameters, but was trained on much less data. And what they found was Chinchilla, which is a model with many fewer parameters than Gopher, but was trained on longer on more data, outperforms it all the time. And that's because they chose the optimal point on these curves. So it kind of proved that these scaling laws that they came up with in this paper, or measured, I should say, in this paper, matter. They proved that you could get a smaller model trained for longer could outperform a large model. And that was a big deal. It is still a big deal.
So in terms of just the flow of the paper almost, and how they did the research and how they came up with the paper, are they doing mostly kind of theoretical work or database work and trying to find, because there's a lot of graphs with a lot of kind of curves and efficiency curves in there. So the first part is talking about all of that. And then when they get to the model, they're actually building a model based on everything that they've discovered. Is that the right way to think about the whole process?
That's right. So this is actually a very empirically motivated paper. And by that, I mean, they just did the experiment. They went out and trained a whole bunch of models. And that's one of the things that you get to do if you're DeepMind or OpenAI, is you can train a whole bunch of models, very large models, right? This is basically training a whole bunch of large models in different settings, with more data or with more parameters, and seeing what kind of a curve that makes. And so they literally just went out and did the experiment. They measured where that point was. And as you say, then they used that measurement to say, okay, well, given what we've learned, we fit some curve to it. We get some constants, we get some parameters out of those curves. And we say, okay, we'll take Gopher's compute budget and we'll allocate it the way we have determined is now optimal. Do we get better performance? That's the flow of the paper.
That makes a lot of sense. They also said that there were a bunch of things in there that they didn't end up addressing. They mentioned learning rate schedule, batch size, optimizer, width to depth ratio. Are any of those important to understand? And do any of those, would Chinchilla 2 that actually focuses on one or more of those lead to bigger improvements, or were they able to dismiss those as super valuable?
I think the most correct answer I could give here is they focused on the most important, most obvious things here, which is just data and parameters. Those are the most easily measurable things. You can vary them very easily. And this is probably the experiment that most people were interested in at the time. Since then, we have seen research into some of those other things. So wider versus deeper has been receiving some attention lately, although people are kind of skeptical about the latest results there.
And what is wider versus deeper? What is the width and depth that we're measuring?
So depth is number of layers, as we discussed last time. Yep. Stack. Whereas wider is more parameters per layer. Just go wider, maybe more attention heads, a wider MLP, anything like that. So that's what's meant by deeper versus wider.
Got it. DeepMind, I think, open sourced AlphaFold. They are open sourcing, or that the results of Alpha, they open sourced a piece of it. They published this paper. Is there a reason that if these different groups are competing, that DeepMind is saying hey, world, by the way, you're all wasting a lot of money. Instead of us just not wasting a lot of money, we're going to tell you all to not waste a lot of money, your computer, or whatever else?
Actually, that's a very astute thing to pick up on. And it kind of leans into a little bit of the politics of AI, or at least the things that go beyond the simple science of it, right? And like you said, a paper like this impacts what people think of and what they know about their ability to train this sort of model. And so in some ways, this is Google saying like, actually, you could get away with fewer compute resources than we have. You can just, if you have access to this much, you can get pretty close to optimal. And I've heard industry scuttlebutt one way and the other way, which says that maybe this is something that other groups didn't want the world to know about for that reason. And so this is probably, you can look at it as one of the first kind of moves in this like great game of AI, which we're starting to see play out with all kinds of new entrants and existing places and everything like that. It's a really interesting time to be around.
Yeah. What do you think defines that great game? Because like the next question, obviously, or at least the one that comes to my mind is, if you're willing to tell people how to do everything as efficiently as you're doing it, and you're owned by a company that has a profit motive, there's like a competitive battlefield somewhere else. Like, where do these people view the competitive battlefield to be? Is there just so much space that they don't care yet? Or like, what's like the next level of that game?
That's a really good question. There's so many different factions with interests in this. So for example, I would say that most scientists working in AI today are like earnestly interested in AI progress and making AI progress happen. There's other concerns also among scientists. There are safety concerns, for example, like, is deploying this model the right thing for the world? But ultimately, the scientists are mostly interested in the science, right? They're not actually as interested in the profit motive of the holding company. And so they want to get the information out there. That's the default scientific thing to do. On the other hand, if like you are a company that wants to make profit, you kind of want to be the person who owns the model. So I still think there's still like a lot of value in just owning the most compute. And so you will probably have the best model, because remember, this is optimal relative to the amount of compute that you'll have. It's not optimal globally. If you're able to amass as many GPUs as, say, OpenAI or DeepMind, you might be able to also get an optimal model, but that seems very unlikely, especially in today's climate. So they still have an advantage there, and they're still happy to release these results because they're probably still going to have the best model. So from a competitive perspective, that's another reason why you might want to put it out there. And you might want to apply, more pressure on your competition because you feel like you will make progress in other directions that you're better suited for than they are, right? Like if you're driving costs down for the industry, that's bad for your competition, and it could be good for you if you're better and more efficient at getting margin.
Yeah. Is there a piece of this that is, obviously there's a fear about one or two companies ending up owning this space. And so you can point to the fact that like, hey, we've actually like published how we do all of this stuff. Like if you're worried about that, government, go fund 100 startups and buy them GPUs and bring more chip manufacturing to the, like there's other, we're not completely locked in here and we're telling you how to do a lot of the stuff we're doing.
Yeah. And I think you could look at this as a piece of that. It's kind of hard to, it's hard to imagine. Like this is a little bit inside baseball, right? Like I can't really speak to how government is thinking about this or in which direction, the various groups want to push regulators. I know that a number of people have been in DC, in Washington, DC lately, sort of talking to politicians about like, this is how you need to start thinking about this. It's really important that you start thinking about this large masses of compute all being in one place. But it's unclear which way that will go or what to do, or if there will be like universal basic compute out there for AI startups. I don't know. Traditionally, the way the government has done this has been through defense funding as well. And I'm wondering if sort of that's not the lever that people are trying to push as well with respect to sort of China and the chips and everything like that.
I think we're going to add this where we do a little bit of inside baseball on the industry every week, because I really like that. Going back to the content, like the thing I think that struck me the most out of all of this is like, as I was going through and trying to like work my way through the formulas and all the charts and all of that, the answer ended up being that they should just kind of scale the number of parameters and the data proportionately. Like, is that a coincidence, or like what is happening there? There's like all this complexity and then out comes this like very simple answer.
Yeah. So again, these were very empirical experiments. Like I said, they just went out and like actually measured it, right? I don't think we have a way of arriving at that conclusion any other way than going out and doing the experiment right now. Because like I mentioned in the Kaplan paper, they believed something else. They thought, no, just scale parameters, just scale parameters as hard as you possibly can. And this paper, the Chinchilla paper, says, no, you have to scale data in proportion. Otherwise, you get diminishing returns very, very quickly. I think it is kind of surprising, but at the same time, it's intuitively correct. But I think what this really points to is the fact that we don't have good engineering principles around this right now. We don't know how we get to this law, if it is a law. We don't know what causes it to be like that. We can guess, but we're not sure. And that kind of points to this whole aspect of, broadly speaking, this model interpretability piece, where we don't really know how we get the performance we do, except in the most broad terms. And I feel like work like this work and other works that are coming out or have come out recently, which kind of just doing the empirical testing is maybe our first step to arriving at some of those principles where we can actually start to make trade-offs in principled ways. But yeah, I think the answer is it happens to be that way. We don't know why, and we don't really even know enough to say if it's a coincidence or not. Intuitively, I would say, okay, seems reasonable, but
yeah, it seems reasonable to me too. And it just so that we're very clear on this point, the reason that Kaplan was the thing that everybody was following, and then this paper comes out and is like, no, that was actually wrong, but we actually have more confidence in this one, is because Kaplan was just saying what happens when you add more size.
Exactly.
And so yeah, they got better. And so whatever, but this is actually trying to find the optimal point. And so you can trust that a little bit more because it's making trade-offs.
That's right. Yeah, I think that's actually a good way to look at it too. Kaplan says okay, how much does the marginal parameter improve our model performance, right? For a given, for compute. And this one says, no, well, okay, how much does data matter with respect to that? Again, there are some there's some scuttlebutt out there that even around 2020, this was actually an already known thing. And I wonder at sort of if there was a battle behind closed doors to get this out, get this published.
The documentary on this one day is going to be very intriguing.
Yeah, the AI is going to write it, and they can probably make it full 3D, and you can interact with the characters. It's going to be sick.
Oh, I saw that now we can just think it, right? So
yeah.
That's great. I talked to somebody else, Alice Albrecht, who's been in the space for a while too, and she's like, we can do this with an MRI since 2008. It's very, we could read it's very cool now that you can turn that into an image, but
yeah,
we're not that close to being able to think up a movie yet.
Not quite.
I'm sure we'll get there at some point. There's a new, we need an alarm or something at this point, new model type or architecture alert that they mentioned here that I don't think we discussed last time. So they said that we talked about transformers. They said something else called a mixture of expert model. What is that?
Yes. Yeah. A mixture of experts model is actually a very classical idea from machine learning. So a mixture of experts model is, in broad strokes, again, a bunch of models that more or less vote on what the prediction should be, or you average out what the prediction should be based on what this collection of models are saying. And again, this is at a very high level, and Noam Shazir, if he was here, would be yelling at me, but at a high level, that's about right. And so the mixture of experts that they mention here is this, I forget exactly what it's called. I think it might be something like absurdly large models or something like that. That's where they introduce basically mixture of experts for large language models, and they're look, it's doing something. It's absurdly large, and it has an effect. And I actually think the thing that is alluding to is more okay, these are scaling laws for transformer-based large language models. We maybe shouldn't take it as gospel that this is always going to be true forever, or that other architectures won't have different scaling laws. But I think another interesting way to look at this is looking for better architectures, looking for better topologies is about finding better scaling laws. It's almost like a dual problem of one of the other. So it's how do you optimally use compute and data to get a better result? So if your architecture is better, it should have better scaling laws. It should have a better optimal point.
Interesting. So that's the thing that if there's a North Star, that's kind of how you, yeah.
There's another problem kind of hiding here in plain sight, which is, and this has been going on for a little while now, where we're kind of starting to saturate benchmarks. And what I mean by that is model performance on the benchmarks that we have for these generative text models is, it seems to be petering out, saturating, right? But qualitatively, the performance is definitely still improving. You can play with them and you feel that it's getting better, right? You can tell as a human it's getting better. And I was a bit skeptical of this at first, but then, I kind of like really paid attention myself. And I think that that's true. And that means that something interesting here is happening. It might be that like the things that they measured for optimality here may also be being surpassed. And it might be, at some point needs to be revisited. But how do we measure the performance of these models is like a big open question now. It's just, we have like, on the one hand, we have like loss, and loss, which we talked about last time, is literally just the difference between your prediction and the target prediction. And for most text models, it's, they're trained on sequences of text, and then they need to predict and fill in the gaps. And that's fine. And you can measure loss, but loss is kind of this thing that you already control. Yeah. So, you can make the loss go up, go down, be a different value, whatever you want. The thing is, you need some benchmarks, you need some tasks outside of the model training to actually say if you're doing well or not. And you can also proxy it by like loss on some holdout set, but that doesn't actually proxy you for the thing you want to do, for like the actual performance. And so because we're starting to saturate some of these text benchmarks, even though like the performances on these benchmarks is not like, wow, that's earth shattering. They're not saturated in the sense that they're like 100% completed. It's more like it's not getting better on these benchmarks, but it seems to be getting qualitatively better still. So what's going on? That's another thing to pay attention to here. Like, what does optimal actually mean?
What do you think, and knowing that maybe you'll get yelled at for guessing, but what do you think is going on?
I think a lot of the benchmarks that we have are out of date. I think it's very difficult to make a good benchmark, especially in this space, because so much of our feeling about what language is like it's like this pretty fuzzy thing, right? Whereas a lot of the benchmarks are very like specific things. And then, I'll give you an example. It's very hard in a text benchmark to measure something like, you want the model to give you like a concrete answer, right? But it might give you an answer in a different way. It's like, what is the tallest structure in the ancient world, right? And your benchmark might have like one answer for that. They might say, oh, it was the Great Pyramid of Giza. But your model might tell you like more things than that, or slightly different things than that. They might say, well, in ancient China, it was this. In Europe, it was this. In Africa, it was this. And again, I haven't seen it do that, but it's just an example. So it's like, how do you measure whether the answer was right or not even? So these benchmarks are very hard to put together. You need so much data as well that they're difficult to generate in the first place. And then because you need to generate them at very large scale, it means that you now have this enormous pile of data that you now need to assess and evaluate. And so you're not sure what's even in the benchmark. It's just a really, really hard problem. Although another thing that we've been seeing, and a few people, there's been a paper out just recently about this with respect to generative image models, which is like, here are some clear things that they can't do. Like, we've created this benchmark by like adversarially figuring out what stuff an ordinary person clearly understands that they don't understand. And that might be a way around it. It might be to just continue like finding and creating these adversarial benchmarks and then beating them while making sure we're still doing okay on the previous ones. This is like a tough problem in ML generally, not just in text modeling.
And I know in here they had mentioned a bunch of different, like hundreds of evaluation tasks that they ran the models through, including things like high school chemistry. Is that as simple as like they took a high school chemistry test and they gave it to the model and they saw what did better? 70s, which is pretty good.
It's pretty good. It's pretty good. There's a lot of stuff like that. And the other thing is like, these are not fine-tuned versions of the model either.
Right.
It's like, there's probably a little bit of prompt engineering that goes on. And then it's like just literally just the question from the test. And then like a human grades the test like they would a person.
And then, so that example, the example, like the tallest ancient building is another one where like, you can at least kind of find an answer, but you're right. Like there's another qualitative piece to language, which is like, ask me to describe a cafe and then ask Haruki Murakami to describe a cafe and like which one's better.
Yes.
And, he's obviously going to do it better in a way that I couldn't describe why he does that better. And so I don't know how in the world you begin evaluating that.
Yeah, and I mean, the way that people do evaluate that right now is like just show it to like a bunch of humans and then like aggregate the score. But then like if you don't appreciate Murakami, you might not care for his description of a cafe. You might be like, well, that's not telling me much about the cafe at all. It's telling me about how I feel inside this cafe. It's hard to evaluate. And I don't know, at this point, I don't want to go into like the realm of philosophy of language here, but I think this actually points to something relatively deep. One thing that I'm excited for in our progress on what's broadly called AI is it forces us to think more clearly about what intelligence actually is. It forces us to consider what intelligence actually is. There's this old cliche, which is like, everything that works doesn't get called AI anymore, and if it doesn't, it's AI, right? For a long time, I was like, yeah, that sounds right. But now I've been thinking about it. No, actually, what's going on is we're learning more about what we think of as intelligence and what isn't. That's what I think is really happening. It's like we're actually figuring out what intelligence is. It's not that we're moving the goalposts. It's that our definitions were too broad, and like this doesn't fit for some reason, for some intuitive reason, it doesn't fit. And the arguments that we're having back and forth are actually very valuable to have. Like the people say, oh yeah, you know, like before playing chess was like an AI problem, and now that there are chess engines, it's not AI anymore. I'm like, well, it is. It's a chess playing AI. What's the problem? There's no problem.
Yeah.
I think general intelligence is the question.
Are there any recent examples of things with language models coming out that like we thought were intelligence defining before that you don't think are anymore now that we know more?
Yeah. So you mean, have I gone the other way on anything where it's like, I've thought this task has to be solved by like an intelligence and a language model did it. I'm like, oh, I guess that wasn't really needed intelligence. Honestly, I don't think so. Over the last probably 2 years, since about 2020, I've been pulled more in the direction of AGI being a plausible existing thing, at least for the purposes of like what I think of as cognitive tasks. I think it's now possible. I don't know how close we are. My timeline is, you know, I've said like 10 years for something that'll satisfy my criteria. Although the other thing about this field is like everyone estimates timelines and those timelines end up being overestimates. It just keeps happening over and over again. Like, when will it be able to do this task? And like everyone working on it says, oh yeah, you know, they're all like, they're usually off by like 5 to 10 years. Like
this happens in anything with steep learning curves. The same thing happens in the performance of solar as well. Like famously, any expert in the field underpredicts the growth rate of solar dramatically.
Yeah. I mean, it happened in aviation. It happened even in motor cars, just how quickly we could build roads and get cars to people after the Model T, especially. So it's really exciting, but I've definitely shortened my timelines. And I think part of the reason that I have is because I've reflected a bit more on like, okay, what is intelligence? Like, what do I personally think is intelligence? What evidence would I need to see? And then like backed out of what I think is going to happen. I'm basically more bullish on AGI than I was.
So I have a question on that too, and I feel like I'm becoming Lex Friedman a little bit here, and we're veering away from the paper, but we'll just ask.
As long as it's interesting to people.
Amen. So I read this paper today that was essentially, it was about React, and it was talking about combining a few different, not the programming language, but I think they called the method React, where like they go through and do like the step-by-step questioning that makes a model perform better, but then they combined a couple of other things, and it gets to the spot where like the model can like reason really well and like make connections that you never thought it would have been able to make in the first place. And they were like, that actually kind of is, for all intents and purposes, AGI. Do you think there's like a cutoff point, or do you think that we're going to stumble into AGI in a bunch of different ways like that, where it's like, well, yeah, that's pretty much human intelligence?
Yeah, I've been meaning to write about this in depth just to get my own thinking out. So you're going to get like partially digested thoughts here.
My favorite kind.
And so for me, I think there's a number of criteria. I think that, first of all, anything we consider generally intelligent has to know that it doesn't know something, and then be able to independently, autonomously go and get that information and then integrate that information for the next time. So it's got to be able to autonomously, first it's got to be able to like know that it doesn't know something. It needs to be like, oh no, this is like missing in my knowledge. I'm not confident here at all. Currently, no large model does that. Although there have been like attempts to mostly just ask the model, how confident are you actually in your answer? But a model is like kind of guaranteed to generate a prediction right now, whether it's true or false. Like there was this model that just got released. It was intended to be like for scientific knowledge or whatever. It's called Galactus, something like
that.
Galactica.
I saw this. Yeah,
that's right. Galactica. That's right. But you can like make up nonsense science. Like you can ask it. The one that I really liked that I saw was, when did the Soviet Union send a bear into space? And it's just really good. It like created this Wikipedia page. It was fantastic, but obviously it never happened. So it's like reading about science from a parallel universe sometimes. Or the other really great stuff I've seen is like you ask it for mathematical proofs of things that are not true in math. Like you can ask it to prove that irrational numbers don't exist. And it kind of like, it throws something that looks like math at you, but it's nonsense. It's like complete nonsense. So being able to solve that problem, I think, is like a key criteria. The way I've described it before is what models can do now is model language. So they can make things that read like language does. They very rarely these days make a sentence that doesn't parse as language. Like it doesn't like start babbling or putting in random words in anymore. They don't do that. It's plausibly language, but they don't model reality very well at all. It's really easy to like find ways to make them say nonsense, like things that are transparently either not true or like implausible in the first place, or where it just like copies other examples of the same fantasy. Like they fantasize, they hallucinate a lot.
This has happened. Sorry to interrupt here, but like this is, I think, the point when I saw the Galactica thread. The point that they were making was we're at this really dangerous spot where it's believable that it could possibly be true, and then it's not, and that's like the worst possible spot to be in. Like, I'm imagining a future where I have my like 4 or 5 trusted models or 10 trusted models that are specifically trained for each subject, and I can be like, I read this really interesting thing on imaginary numbers not being real. And then I would like throw my math model at it and be like, is that math good? Because I'm not going to know. Like, you have to be an expert in everything to know when it's really convincing.
All right. So do you want to know something really scary? Do you want to know something really scary? Do you want to hear the cosmic horror scenario here?
Yes.
So the cosmic horror scenario is the universe is fundamentally incomprehensible, and we're going to try to use these models to understand the universe. And then the models are also going to be incomprehensible. And because they're incomprehensible, we're not going to be able to know if anything they're saying is true or not. We're not going to be able to verify it, right? That's the cosmic horror scenario. I don't think it'll be like that. I think that the universe is understandable, but if it's not, we're in deep trouble.
But could you then use like a council of models to like understand, you know, like if one model that you trust a lot makes up gibberish about the truth.
Yeah, but you trust it. You trust it, right? You trust it, but you don't know how far you can trust it, especially when it comes to new facts.
Well, that's what I mean. So if you think you trust it, but you just want to like sense check, couldn't you run like a bunch of different types of models at the same problem? And if they don't all get to the same, you know, truth underlying the universe, at least you know not to trust any of them?
Well, I mean, like, unless they're pathologically wrong all in the same way, right?
Yeah.
Like for example, for a general intelligence should also be able to create new facts about the world on its own. That's another thing that I think. Like, it can go looking for something it doesn't know. If the thing that it doesn't know doesn't already exist, like it can't read a book like you and I can, you know, it should figure out how it can decide whether something is true or not. That's important for general intelligence. Even animals do that.
Yeah.
Right? Animals like figure out if something they believe is true or false. They'll check under a rock, for example. They'll like sniff around if there was a snake or not, because they don't want there to be a snake. They want to know, so they need to do an experiment. So general intelligence needs to have that capability to sort of autonomously get facts about the world and ingest them and like keep them in its memory. The other thing that it needs to do is function continuously. So right now we have these models. They have, you know, what are called context windows, and as far as the model is concerned, the entire world exists in that context window. When you put a new thing in there, everything is gone. It doesn't know anything anymore. It only knows what's in the context window. And you can make pretty good progress by like compressing and summarizing other things that it's said and putting them back in the context window and doing another completion. But it's not how intelligences work in the real world. You and I, like, okay, we have a context window over the length of our lifetime, but that's not really how our mind works. I'm not thinking about my entire life from when I was a baby to figure out what I'm going to say to you next. It's clearly not how intelligence works. So any kind of general intelligence probably needs to have the capability to have this like continuously shifting context window without like losing its understanding of the world. People have been working on that. There have been like approaches to making very large or even infinitely long context windows with a few new architectures. There's a very exciting architecture called S4, which is, I think, called the structured state space, and I forget what the other S is for, model, which generalizes like input sequences and does some really neat stuff, which is exciting. But I still think that like it's not how it works. Making the context window longer is not really how intelligence works.
So it reminds me of listening to the, speaking of AGI, but the John Carmack, and gosh, I'd listened to too much Lex Friedman, but like, just, I think when he was talking about how they figured out how to make levels that you could just keep walking through, and then like the wall just kept appearing. Like it doesn't mean that you're in the real world or that like that is now the metaverse or whatever, but it does feel like the idea of the context window just kind of moving with you, even if it's not getting to real intelligence, you can at least like get a little bit closer to that.
Yeah, I think these capabilities are active areas of research. So I'm pretty bullish. I think, you know, order 10 years we'll have something that I have to acknowledge is AGI. That's where I think we're headed.
That's unbelievable. And I think we need to save the implications, whether we think this is good or bad, whether we're scared for the next one, to leave people hanging a little bit. But I think there's a good kind of entry point to this, which is, you know, if you're talking about the model being able to go kind of answer its own questions and find things anywhere, like, and going back to Chinchilla, the fact that like they need a lot more data.
Yes.
Like,
yeah.
The ideal thing, I guess, would be, although there's questions that I'm going to get to as well, if you could just give it like all of the data known to the universe, starting with everything that's public on the internet and then everything private on the internet, and then figuring out how to translate the real world into bits and bytes. But in the absence of that, like when we want to make data sets 10 times bigger, like where is that data coming from? Do you have diminishing quality of the data? Like that seemed like a big thing to me. It's like, we need a lot more data. Where does that all come from?
Yeah, right now, this is the question. So here's something interesting. The thing that I just dropped in the chat, it's this great post from a forum called Less Wrong, and from, you know, cross-posted from the AI alignment forum. Some people are going to instinctually cringe at the fact that I'm linking out to Less Wrong. I urge them to read this because it's actually really interesting.
I think that whole movement was canceled in the past week or so.
Yeah. So. Well, it's the sort of the FTX contagion is going to have surprising outcomes, I think.
Yeah.
But you know, to be fair, I actually think that most people in that group are very sincere, and some of them are quite smart.
As do I.
So I don't want to badmouth them.
Yeah. No, we're going to overreact to it.
No, of course, it's going to swing in like the wrong direction. It's going to be very silly.
Yes.
This blog post that I've just sent you here covers like a bunch of this stuff. They're like, okay, well, how much data do we actually have? Like, what's the best model we can get given how much data we know we have and given how much compute we know we have, like globally available, right? And where is it coming from? And you know, they come to some interesting results. I won't summarize them here, but it's like pretty interesting. They also do this thing where they're like, okay, well, like let's just push data to infinity. Let's just put D in the limit to infinity. Like, but keeping compute constant. How good could we get in principle with infinite data? And you know, they come to a conclusion. It's actually really interesting. And they look at these different architectures and they're like, okay, well, infinite parameters or infinite data, like just pushing out these things to the logical conclusions from the scaling laws. And it's nice because there's like finite performance, because the way that the models are set up is like it asymptotes. So on the one hand, like more data has diminishing returns in these architectures as well, which is why, as we said earlier, like we need better scaling laws, which means we need better architectures. But getting back to your actual question, like what is the data and where are we going to get more data? This is kind of a problem at this point. In some sense, we're starting to saturate the available data sets as well. We've like all available text on the web, or like very close to it.
This is what Elon's doing. Holy shit. So if you grow Twitter usage by 10x, there's just a constant new stream of text data on every current thing. I'm doing God's work as a Substack writer.
Tweeting is immanentizing the AGI advent. Yes.
You're welcome,
tweeting
humanity.
will make the AI come faster. So we're all doing good work out on these streets online. So this is like a big question. Like right now is like, the other thing is like web text data is like fine. It's actually pretty heavily biased in a lot of ways as well, because it's whatever people talk about on the internet. And frankly, a lot of the things that people talk about on the internet are stupid bullshit. Like they're fun to talk about, but they're not interesting or serious. But what the contents of the data are do matter. I'll get to that in a bit. There's also like a bunch of data that we can't get to that's locked up in other places. There's still more to ingest. We can like ingest every book. Because Google did a good job like OCRing and like every book that they got their hands on, and the Library of Congress has a lot of stuff available. And there's a data set called Pile, which I think is like a meta collection of like a whole bunch of text data sets, which I think is the default for everyone right now. And then we have stuff like code, because GitHub, brought code out, and people were able to use that to train code-based models. And we have a bunch of text, but there's a lot of data that's like locked up. Like a lot of technical stuff is locked up. A lot of scientific stuff is locked up or difficult to come by. So getting at that data is a problem. The one that I always like think about is Autodesk has tons and tons and tons of data sitting around about how people use computer-aided design, CAD software.
Yes.
And they'll never release it. But we could, in principle, train a model to do CAD for us, and that would be huge if Autodesk were so inclined.
I have a company that's building a building model database, and like I think this is probably part of their long-term plan. They have a shorter-term monetization plan, but eventually, if you own the biggest database of at least on the architecture side, but then you need to do parts and all the other types of things.
Yeah, it's really tough. But the point is like a lot of this data is like in principle there, but not available. And then there's tons of data that's not available. Then you have the other problem, which is like the time keeps going forward. More data keeps getting created, even just web data, even like Twitter, like you said. And so what are we going to do? We can't necessarily afford to like retrain these models every year, especially not if we want them to get better, right? So we have to figure out a way to basically continuously improve them without losing any of the capabilities they already have. But like the question is like, where do you get data? YouTube, for example, is locked up. I mean, YouTube is kind of a copyright minefield, right?
True.
OpenAI were able to do this thing. It's called video pre-training. It's a very interesting paper for some of my other stuff, where they were able to use Minecraft videos from YouTube to like train a Minecraft playing bot. And it's more complicated than that, but that's what they did. But they were able to do that because Microsoft owns the copyright to Minecraft, so they own the Minecraft videos on YouTube. So Microsoft could just, here you go, OpenAI, have the things you have copyright to. You can't do that with YouTube in general. It's locked up behind IP law.
And Spotify, and like this is the challenge with music, right? Like it's not as much that it's like technically really, really difficult. It's like you can't, or is it both?
I mean, music is technically challenging. It's really hard. Most music generative models are not great right now, but it's unclear how much of that is just the data issue.
Yeah.
And I think this, like, it ties into this really interesting problem, which we're also going to see litigated over the next few years, is like, if you feed copyrighted stuff into your model, and like, are the generations of that model, are they somehow linked to the copyright or not? And then the other question is like, what if you didn't have any copyrighted things in your data set, but it produces something identical to a copyrighted work?
I had not thought of that one. That's interesting.
What do you do? Like, strictly speaking, nobody made it.
To the first one, like this is what UBI should be almost, right? Over time, as these models do more things that humans do based on the inputs that humans have put out onto the internet and whatever other data sources that they're ingesting. And like, there's nothing left for us to do. And I think we always find new jobs and all of that. But as an extreme case, like I should get a cent or whatever, my proportion for every time like my output is used commercially in a model based on something that I've written on Not Boring. And that's a tracking nightmare. And like, there's all those types of things, but I don't love the battle between like, poor Greg Rutkowski and like all the people who are using his name in these prompts were like, he's not getting anything from this except a little exposure. Where it's like, I wish there was just a way to like pay Greg Rutkowski 10 cents every time his name is used in a prompt.
But look, this is the same problem as like how do creators get paid on platforms, right? It's exactly the same problem. Like I'm generating Twitter revenue, but I don't get paid to tweet. Some people would pay me not to tweet, I think, but I'm not getting paid to tweet. But I am generating revenue for Twitter, right?
You're opting in a little, you're opting into that system.
You're right. But my point is more like that problem is in part business, but also in part technical.
Yes.
Like how do you apportion my cut of Twitter's ad revenue, right? Like it's very hard. You can't do it, or at least we don't know how. These days I hesitate to say we can't do something because like 2 years later it turns out we can just do it. So.
I'm not technical, so I think all this stuff is easy, right? But like Twitter also has every motive in the world to say like that's impossible. We have no idea.
Yeah, of course,
or whoever else. And it feels like if that were business critical for them to figure out, they'd be able to like come up with some attribution model that's like, all right, I don't know,
Yeah.
people spend X amount of time looking at Packy stuff, and whenever we show people, because there's certain people that when they show on my app that like up top that person has tweeted, you know, they just like show the little profile preview.
Yeah.
I'm like definitely more likely to click faster. So like there are ways, I am sure, that they could figure out some way to figure out who drives the time spent on Twitter.
Look, maybe we can ask the AI in a couple of years. It'll be like, how do we divide our revenue between all the people? And it'll be like this. And then we won't be able to know if it's telling the truth or not, but we'll, you know, we might use its output. We'll see. I don't know. But that's another thing, talking about like the social implications of a bunch of this stuff. And you kind of, I actually don't think that like, oh, everyone's jobs are going to get automated away is the big thing to worry about. I worry about other things. I worry about this as a media technology. But the thing that I was thinking about is like, it's like AI washing, I think, is going to become a thing. And what I mean by that is like, no, it's not us. We're not evil. This is what the AI objectively said is true. The thing is like, as these things become more general purpose, as they demonstrate more capabilities, it gets easier for the average person to believe that that's true.
Totally.
Right? Because it kind of sounds like nonsense. Like the argument that I would make if I was trying to swindle people, I'd be like, no, it's just math. It's objectively true. Like you can't argue with multiplication, right?
Totally.
If I wanted to swindle people. But that's not the reality of it. It's not actually how any of this works. And I think that like we're going to see the first instances of AI washing in the next few years. I think we're going to see people be like doing something bad, but hiding behind like the computer did it.
You anticipated a question, and this one's a little philosophical as well, that came out of this paper, which somehow, and I don't think had planned for this to be the case at all, but Chinchilla ends up being less sexist than Gopher, but like pretty much as toxic as Gopher. And so like one of the ideas is like, how do you make sure that the data that you're feeding it isn't toxic or isn't sexist or isn't racist? It feels like a little bit of playing God, figuring out like the right data to feed it. Like, how do you think about like which cultural norms are okay for the AI to adopt? If you're YouTube, you can say like, look, this is just or Twitter, this is a mirror on humanity. And you can even more clearly say that here. So like, where do you draw that line, or how do people think about it in the space?
It's an incredibly tough problem, basically. Like, this is a really important question, actually. And we can tie it back to the paper by noting that, again, what we were talking about, right? If you have a lot of compute, you can build a model with better capability, which means that more people are likely to use your model, which means the decision that you use, like decisions you make about what you're feeding that model are going to affect like a very large group of people. But we also don't know the exact effects of balancing the data, the input data one way or another, or filtering the model's outputs one way or another, are going to have, even if we know what our objective is, right? It's fairly straightforward to demonstrate, even for models where the authors have tried really hard to prevent a lot of these biases, it's still possible to make them generate those biases. Like you can just like prompt them slightly differently and still get the bias. We don't really even understand the connection yet. And then even if we did understand the connection exactly, it's like, okay, well, which ones do we choose now? And I think we can actually look at this in terms of like what we already know from Twitter and Facebook and things like that. What tends to happen is the large centralized platforms tend to create norms that are average. And there's this thing called the curse of averages, which is basically saying if you like do the thing for the average person doesn't exist and everyone's going to be mad at you.
Yeah.
Everyone's going to be mad at you. You can't win. So I don't know what we're going to do.
Possible problem. Yeah. It feels like you almost have like a sham world vote. So people like, people feel like they had an input on it or something.
Yep.
But yeah, no, it seems like
elections being what they are these days, I'm not sure people would agree with results even if we had the vote, right? There's so many questions. I think we're in too deep. Exactly. I honestly think that like these are the kinds of issues that are really going to matter, not automating people's jobs away. These are the things that are going to matter about AI. The thing that I always think about is every new media technology that gets introduced, and you can look at text generation, image generation as a new media technology, creates some sort of social upheaval. So the kind of like deep example of this is the invention of the printing press in Europe, creating like some of the worst conflict that's ever been seen, because things that ordinarily wouldn't spread very far got spread very, very far very quickly and destabilized all kinds of political orders and led to things like the 30 Years' War.
I wrote about this in the draft of the paper that I'm writing on Monday from a 2013 Slate Star Codex article. He says that the printing press precipitated the Protestant Reformation, the newspaper, the Renaissance, the scientific revolution, and the rise of nationalism. Like, plus the things that you're saying, the effects are still being felt today.
Mass media technologies do this. And you can look at text and image generators as a mass media technology. So the early wielders of these technologies, the people who are able to effectively use them to influence large groups of people, like that's a dangerous thing. Historically, that's been a very dangerous thing. Historically, like everyone says, this is going to be a great tool for education. That's what everyone says about every new media technology. And the reality of every new media technology is it gets used for propaganda, entertainment, and pornography. Like we would love to believe we would love to believe about ourselves as a species that we are animals that primarily love knowledge. But the reality is most people just want to have a good time or like believe happy things. And that's why propaganda is very effective. And I don't know, we're already starting to see algorithmic propaganda. Like you can use ad targeting to do this stuff.
Yeah.
But now you put AI behind that and like you can fine tune the AI where it can like customize the propaganda stream down to the individual person. I don't know what's going to happen. It's a little frightening.
I also don't think that the AI is going to take our jobs. I think that's every time that fear has been had in history, it ends up not being true and we end up doing cooler things. I do think what's happened, I mean, even with like a YouTube, I was reading this post the other day, like that there's just this decentralization mirage. And like, you think that the internet's this decentralizing force, but instead of a teacher being able to teach 20 people at a time, like one person teaches 10 million people how to do something on YouTube. It feels like that gets amplified. If there becomes like, we all use GPT-4 and like, whatever it draws from on a particular topic, like there's 5 people that like are the best and that it, I don't know if it even works and you can tell me if it doesn't that way, but like over time you can see that if like there's just stuff that are inputs that are much, much, much better, then like everybody's concentrated on this one place. That gets even more extreme.
Yeah. So that's the other thing with mass media technologies is because they reduce the distributional frictions to 0. You have these power laws over outcomes, right? Like 1,000 years ago, the best musician like in the world, probably like 1,000 people knew that person, right? 1,000 years ago. And we know them, like they're popular today because this is actually funny. Like some artists have become more popular than in their own time by like orders of magnitude, even as a total fraction of the population of the earth, because we were able to preserve them in some way or another. So like we have, Mozart's sheet music or whatever. And then the mass media technology like later resurrects them. And then every human being on earth knows Mozart. Whereas before, like, I don't know, a few thousand people, maybe. So, and what I mean, what that ends up in is like, okay, there's like one best person, right, in the entire world. And everyone's eyes are just going to be focused on that one best person or like the top, like whatever sliver of a percentage it is. That tends to happen whenever you have mass media, like attention gets concentrated because distribution like goes away. And it's like, you can think about it as like the tournament for talent gets globalized. And then whatever, the most popular thing rises to the top, which is, by the way, not necessarily the best thing at all a lot of the time.
Totally.
But it is the, like in expectation, the thing that people think are best. So
here's, I guess, another basic question that I have on these data sets. So like, I would imagine my emails are not available and being used in data sets. Maybe I
don't think your emails are, no.
Good. All right. Maybe my Substack is because it's a free open newsletter. If I have a paywall, does it respect the paywall? Does it go behind the paywall?
I don't know. You have to read the license agreement for your Substack. I don't know.
The reason that I'm asking is I wonder if there's going to be a spot where like not me, but somebody with like a much, much, much bigger audience who like actually like is the most popular teacher of like some topic ends up just paywalling their stuff and then going to OpenAI to
be like, you can train a model on me.
Yeah, be like, train it on me, but you're definitely not getting that shit for free. Like, because I know that this is going to be a huge part of the output for this particular topic.
Yeah, it could be, right? Like, Substack pays a lot of like people, like instead of like you paying Substack pays you money to write on Substack, so more people come to Substack. So that's very plausible to me. But the relationship between the input data and the output is like not clear. It's even less clear than on these like creator platforms. We don't really like, it's trained on billions and billions and billions of data points. And even if it like uses you as the best teacher to fine tune on, it's like how much of that is attributable to you? We don't know. We can try it. Like you can think of ways to like try it out. You can say, okay, this is what the model does without Packy, and this is what the model does with Packy. And the difference is like what we pay you.
God,
somehow.
I hope that they do end up figuring out a way to pay people for their contributions here, because I think like that would be an incredibly great motivator for people to try novel ways of becoming the very best at a particular thing in a way that like the internet has already kind of done, but it would like really incentivize people to try like to leap over other people, because you could become a billionaire if your thing is like very clearly like driving the outputs of a model.
Yeah. Which is again like another facet of this like power scaling in mass media technologies. Like, you know, you've got billionaire YouTubers out there.
Yeah.
Right. It's the same kind of the same thing. It's like I drive so much ad revenue for you that I can be a billionaire. Like it's a possibility. I don't know what the shape of it is. I think that it's a very exciting time. I think that we're going to learn a lot. I think a lot of it is going to be dangerous, but like survivably dangerous. We'll just kind of have to see what happens. I don't really think we have a choice at this point. Like we kind of have to strap in, and I wouldn't say, I hate to say hope for the best, because that makes people like not feel like they just have to take whatever's going to happen. No, it's like be prepared. Like think about it. Think about what you want to do and who you want to be, and that kind of with the things that are coming. Be aware of it, but also like don't panic. Don't like get outsized ideas. You know.
Yeah, I agree. To wrap up here, so this paper looks like it was published on March 29th, 2022. So we're about 7 or 8 months after the publishing of this paper, 7.5 months after the publishing of this paper.
It feels like 5 years, honestly. Like,
well, that's what I was going to ask. So like,
I was like, when did this come out?
So in terms of like production models, like where is this having an impact already? Is this shaping like the next generation of things coming out? Like, are we using things that are based on Chinchilla now? Like, what is the impact of this paper so far, and what do you think it'll be?
Yeah, I think that since the publication of this paper, pretty much everyone training large models of one kind or another has made references to whether or not their thing fits the scaling laws, or why they chose a certain amount of data, a certain amount of parameters, arguing for, you know, their amount of compute or whatever. Some people have like pushed the boundaries a little bit and shown that like, okay, for this architecture, this is a scaling law. For this other architecture, this is like slightly different scaling law. I think in many cases, the models that are in production right now are probably, you know, optimal with respect to the Chinchilla laws. I can't speak to the next generation of what's coming, because they may involve breakthroughs that like take us off these rails. I don't know. I can't speak to that. I'm
under NDA with OpenAI. No, I'm kidding.
Well, yeah, I mean, like if I did know, which I don't, I wouldn't be able to talk about it anyway. Yeah. But I honestly don't know. Please don't come after me, Sam. I seriously don't know. Yeah, like I can't speak to that. I think that if you found a way to break the scaling laws, you probably would want to keep it a secret until you were the first deployment of that model. And also, it's like very hard to detect if you broke the scaling laws or not. That's the other thing. From the outside, it's hard to tell.
Right. Did DeepMind, and I guess I already told you last question. So I know they made Chinchilla as part of this paper. Are there any DeepMind models out there that just regular people are using that leverage this, that like came out first from DeepMind?
So that's interesting. What regular people are using in practice is hard to say. I think it like the way that Google versus DeepMind do things with versus OpenAI, the way they do things with their models is slightly different. So you can't really open a Palm playground today, whereas you can open a GPT-3 playground. And like Palm is compute and data optimal. It does in principle better than Chinchilla. It like climb that curve. Palm is like the big language model that Google has. So I can't really speak to regular people, but definitely there are probably models in production that are being used in at least some products, maybe. That's another part of the politics here. Like in a lot of cases, it's difficult for product organizations to absorb a large model like this, like seamlessly and flawlessly. It's just a difficult problem from an engineering perspective and from a product perspective. So it's hard to say. It's honestly like, I understand that that's kind of like a wishy-washy answer, but it's hard to say.
No, the wishy-washy is good as long as it's the truth. All right, so I'm gonna do my like 2 second did I understand this
Yeah.
recap. 2 second did I understand this recap of Chinchilla. They looked back, they did a lot of analysis on existing models and did a lot of work on kind of what's best practice before they looked at Kaplan et al, which said just make the models bigger, and if you do that, actually performance scales with the number of parameters. And they said great, but what if you have a limited compute budget? How do you get the balance right between parameters and the data, holding compute constant or at different levels of compute?
Yeah.
And the way that they do that is you scale your parameters and your data proportionately. And that's the best way to get a compute budget optimal model. And so now the question is, great, everybody went really hard in the direction of making the models bigger. Now, how do we get good data to add more data to those models and balance that out?
Yep. Yeah, that's right. That's right. The way to think about that is like scaling parameters gives you diminishing returns in performance. And for a given amount of compute, scaling parameters gives you diminishing performance without more data. And it turns out if you measure like those diminishing returns to parameters and data, if you increase both equally, such that like your compute is like optimally divided between training time and number of parameters, that's in some sense optimal. In some sense optimal for the kinds of transformer-based large language models we have now.
Hell yeah. Well, Anton, thank you for teaching me about Chinchilla. Everybody, our huge and growing subscriber base, thank you for joining us here on another installment of Anton Teaches Packy AI. We'll be back in about a week. The last time we teased this paper. This time we're going to have to talk offline and figure out where to go next with this.
I have some ideas. I think we've been sitting at the edge of AI research, like, you know, papers from 2022. I want to go into like the history, where we came from, like how we got here. And I think a really good paper to talk about is like the first perceptron. I think that would be a really interesting thing to talk about as like a platform for understanding like how did we start down this road.
Is the paper called The First Perceptron?
No, I don't know what it's called. I have to go look it up, because back then papers all had like really long titles, and the thing that they actually did was not in the title.
Got it.
So I have to go look this up. But I think taking a look at that, like from the prehistory of AI, I think would be really interesting.
I love that. Let's do it. And I'm going to just call the episode The First Perceptron, because that's an incredibly cool name. So join us next week.
Doesn't Perceptron sound cool?
Perceptron sounds like the Eye of Sauron kind of, but
yeah. Like Transformer, like
yeah.
All right, Packy. This was great.
This was awesome. Thank you, Anton.
Next time. Bye-bye.